Here we go, everybody. We did it. Final lesson 13.5, sample means, margin of error, confidence intervals, and we are officially done with these videos to get us out of this COVID-19 teaching style. Okay, so for those of you still with us, congratulations. So here we go. Let's finish it up. So sampling variability. What we have here is what makes learning from sample data challenge is that different samples from the same population give different results. So what they're showing here is, say you randomly chose any numbers between 1 and 99, okay? So you have 100 numbers to choose from. And they're saying, well, the mean of that, the average of that would be 50, because half of that is 50. If you randomly chose 10 numbers, does that mean that the average is always going to be exactly 50? And that's what they're showing you here, is they took 8 samples, okay, here are the 8 samples, and then here are the 10 numbers, random numbers that were chosen, okay, and then, my computer's skipping around here, and then they recorded the mean. And then the sample mean here is 48.4, 50.4, 54.1. So they're all pretty close to 50, but none of them are exactly 50, and that's kind of what they were trying to explain up here in that paragraph. So the value of the sample mean varies from sample to sample, and that's it. This is your sample mean. Although the values in each sample differ, their means are clustered close to the actual mean of 50. So what do you think would happen to the sampling mean if we increase the sample size in each sample? So what that's saying is we're still going to do 8 samples, but maybe we're not going to choose 10 numbers. Maybe we can choose 20 numbers or 30 numbers or 40 numbers. That's what it means to increase sample size. Well, if we increase sample size, increasing sample size would allow the sample mean to get closer to 50, which is the actual mean. Okay, so the more people or the more numbers that you choose, the closer that you're going to get to the actual mean being 50. All right, so now here's another similar situation of flipping a coin. Okay, so they did 4 tests here. Okay, and what they're showing is in each test, they're recording the number of head, and here they did 20 trials of tossing a coin 50 times. Here they did 40 trials of tossing a coin 50 times. The third one, they tossed it 60 and 80 times, and they recorded the data. So in this one, the mean was 25.45, and the standard deviation was 3.8. The mean was 25.25, and the standard deviation was 3.4. Okay, and they're recording that data, and then here it's when they tossed it 60 times, it was 24.5 with a standard deviation of 3.11, and here the mean was 24.813 with a standard deviation of 3.175. So the dots are showing each one of the samples. So if you looked at this one, it's kind of, it shows like a little bit of a curve, but it's a little bit more flat. And then as we start increasing the sample size, we're going to start to see that it's going to start to become a little bit more and more like what we started to learn is a normal distribution curve. Okay, and that's what they're showing you here. And if you looked at each one of those means, they are getting closer and closer to the actual mean, which is around 24 they're showing here, because you're depending on how many times you're tossing it, right? So as the sample size was increasing, the sample mean tends to follow a normal distribution. As the sample size increases, the sample mean gets closer to the true mean, or as we said before, the actual mean. As the sample size increases, the standard deviation gets smaller, okay, which means that those numbers are clustering closer and closer together. Okay. Inferential statistics are used to draw conclusions about the population using a sample, and basically what they're saying is, okay, to try to make it a little bit more easy to understand, if I did a survey in, say, Central Islip School of what's your favorite artist, that would be my sample, or your favorite rapper, whatever the case is, and then they could use that sample to draw conclusions about maybe everyone on Long Island, something like that. And that now starts to bring in margin of error, which would be an interval from the expected proportion that is likely to contain the majority of the data. Let's first pretend like you understand that for a second as I try to dive into it a little bit deeper, and then I can try to bring you back. Okay? So in statistics, it is understand that if the data value is more than 2 standard deviations away from the mean, the data value is unusual. Okay, so we kind of learned about that. So in any normal distribution, how much of the data falls within 2 standard deviations of the mean? So now this is the part that's kind of important, right? So if we looked at the normal distribution curve, okay, it looks something like this. Okay, with your, remember, our mean goes in the center. And then as we start to go away from the mean, right, those are our standard deviations. So this would be 1 standard deviation. This would be going back 1 standard deviation. This is my attempt to make the deviation symbol. Just go with it. Okay, if I went 2 standard deviations, it would be here. 2 standard deviations from the mean would be there. So if we recall, this represented about, what was it, like 13%, right? And then this was about 15, something like that. So basically, they were asking before about how much percentage lies here, and that's about 95%, right? What they were saying up here is that if you are more than 2 standard deviations away, it is considered unusual. Like that usually shouldn't happen, or it doesn't happen, because 95% of it lies within 2 standard deviations. Okay, so now you have what we just talked about, which was the margin of error, and that is the percentage points away from the real population value. And I'm going to make that sound like English in a minute. So the margin of error is the percentage point away from the real population value. Now, a confidence interval is a range of values, like a start and a stop, where we are fairly sure our true value is in. So we then use the margin of error to create a confidence interval. So these two are tied, and this is going to make a lot of sense to you in about 2 seconds. So a confidence interval, again, is a range of values we are sure our true value lies. Okay? Now this comes up a lot in like elections and stuff like that, where they're trying to figure out, oh my goodness, okay, they're trying to figure out where people lie and within what ranges it would be considered acceptable. So let's go back to that thing, that normal thing that maybe made sense to you before about taking a survey of a small sample and kind of relaying that out there for the whole population. So if we went to say, just say one school or maybe a couple of schools on Long Island and asked them what their favorite rapper is, okay, we might get a percentage that likes a certain amount, okay, or a certain rapper. Then we can say, okay, well, let's extrapolate that to the whole population, say, of all of Long Island, and then we could create a margin of error. Okay, now we would want that to be within 2 standard deviations, because this would represent 95%. So our confidence level being of 95%, okay, would fall between that. So it's not giving an exact value. It's kind of getting, all right, so between this percentage is what I believe that the students would like, or something like that. So let's see if this now makes sense when we look at an example of a recent poll that found that 36% of all respondents would vote for candidate A in an election. The poll reported a margin of error of 4%. Give an interpretation of this margin of error means in terms of the 36% support for candidate A. So wherever they did their poll, they said 36% will support or vote for this specific candidate. So does that mean that exactly 36% would vote for candidate A? Well, no. It could fall around 36%. And that's what they talk about in terms of their margin of error. So if they figured 36% is going to vote for A, if there is a margin of error of 4%, that means it could be anywhere from as low as 32% of the people will vote, or as high as 40%. And that would be the confidence interval. Well, we think that between 32 and 40% would vote for candidate A. That's what they're trying to talk about. Okay, so that's kind of what, give an interpretation of what this margin of error means in terms of 36%. So it means you can be above or below the 36%. So about 32 to 40% would vote for candidate A. Okay. So there is everything that we're talking about for margin of error and confidence interval. It's the standard deviation part that's going to be the most important. And that's going to come into play for when we look at exercise 2. So at the beginning of the school year, the district implemented a new physical fitness program. A student project involves monitoring how long it will take for the 10th graders to fun a mile. I'm pretty sure that means they're going to run a mile, maybe for fun. A random sample of 20 students was taken. The sample mean time is currently takes 10th graders to run a mile is 7.9 minutes. So the students doing the project collected 50 random samples of 10 students each and calculated the sample means. The standard deviation of their distribution of 50 sample means was 0.6. Based on this standard deviation, what is the margin of error for their sample mean estimate? Okay, so when they just looked at a small portion of the 10th graders, okay, they set it up here. So it was a random sample of 20. They found that that mean was 7.9, right? 7.9, that's your mean. Then they did a large project and they collected 50 random samples of 10 students each. So that 50 samples, 10, 10, 10, 10, 10, 10, and then they found that the standard deviation was 0.6. So if you moved away, or either above or below, and you moved one standard deviation, you would add 0.6, okay? And then that would be 78.5, right? And then if you went ahead and moved another standard deviation, you would add another 0.6. And the same thing goes here. If you're moving away from and down, you would subtract 7.9 from 0.6, and you're going to end up with 7.3. And then if you went ahead and did it again, you would have 6.7. Subtract 0.6. And here I didn't write 9.1. Okay, so what did I just do there? Okay, I'm sure your reaction is, I have no idea. Well, I basically am trying to show that normal distribution curve. Here is your mean. Here was moving one standard deviation by adding and subtracting 0.6. Here was moving a second standard deviation. Now remember, two standard deviations represents 95% of the data, right? So your margin of error being two standard deviations, or 95%, would range from 6.7 to 9.1. What does that mean? Well, that means that if I went to 10th graders all around the country, I could say with about a 95% confidence rate, okay, I'm 95% sure that a lot of those 10th graders would be able to run a mile between 6.7 and 9.1 minutes, okay? And then I just answered B. So interpret the margin of error you found in the context of this problem, okay? Based on this problem, many 9th graders would be able to run, sorry, this is really sloppy handwriting, between 6.7 and 9.1 minute miles. Okay, so again, we're moving two standard deviations from our mean. All right, turn it over. An ecologist wants to know what percent of the 10,000 fish in a lake are caught. She takes 500 samples of size 50. The average of these samples is 0.24 with a standard deviation of 0.06. Use this data with a 95% confidence interval. We can determine the percent of fish in the lake, which of the following. Okay, so again, looking at that curve here, your average or your mean is 0.24 with your standard deviation moving 0.06. Okay, you add 0.06 and you subtract 0.06. And how many standard deviations represents 95%? And that's 2. So you're going to be adding 0.06 twice, you're going to see subtracting 0.06 twice, and you're going to end up between 0.12, that would be here, 0.12, and then that would be here, 0.36. So 0.24 plus 0.06 plus 0.06 is 0.36, and 0.24 minus 0.06 minus 0.06 is 0.12. So there you go. That would represent our average of the sampling. All right, exercise 4. So Anne has a coin. She does not know if it is a fair coin, which means that it could, with 50% heads, 50% tails, like it's not loaded, it's not going to always land on the same side. So she flipped the coin 100 times and she got 73 out of 100 heads, and she got 27 out of 100 tails. Okay. She ran a computer simulation of 200 samples of 100 fair coins. So then basically the computer did what she did, but did it 200 times. The output of the data, so then here is what it is, right? And then here's kind of our normal distribution right there. Here was your mean, 0.497, that's going to be right here. And then your standard deviation, each one moves 0.05, okay? And then that would be able to show you, okay, where you are being two intervals out, or where that 95% would lie. Okay. Given the results, is the coin fair? So this is recording the heads, right? So we care about this number here. Now that number there is going to be 0.73. So where would 0.73 lie on this curve? And 0.73 would be all the way out here, 0.73. We want to be within 2 standard deviations. To be within 2 standard deviations here, it just doesn't make sense. And it says we just did those notes before. where it says, in statistics, it is understood that if a data value is more than 2 standard deviations away from the mean, the data value is unusual. So the way I'd explain this one is I would say, is the coin fair? No, because the sample mean lies more than 2 standard deviations outside the actual mean. Okay? Bam. Did it. Done. Finished. Finito. Well, that's it for me. Mr. Cornell, signing out.